There we go. At the end of that topic, I made a point to say like, well, okay, here's an activity, but we didn't do the activity. Write the function min, max, and sum, where min is, if you've got a list, write a function of give me back the minimum value from that list. Assuming these are like numbers and things that can be compared. Max, same thing, but don't tell me the smallest, tell me the biggest. And sum, which is just the sum of the contents of that list. Those are functions that already exist in Python. I don't need to write them. But you could write them at this stage. You can write the function. You should be capable of doing all three of these at this stage of the course. If you're not, get on top of it. You should be able to go through and do these if you sat down and you tried. And the reality is, these functions that are given to you for free, the functions, the versions that you write, are going to be effectively the exact same code that was given to you. So we're at the stage where you know enough that you could be writing code that Python gives you for free, sophisticated code that you get for free that's handy. Like, you can do this now. You have all those skills. And, I mean, really, the three of these are all kind of, when you break it down, these three functions are all basically linear searches. Or at least doing a linear iteration through some collection, like a list. Find the min. Well, you're doing a linear search, not for a specific item, but for the largest element in that list. Min, the smallest. Sum, okay, you're not searching, but you're going over it and just taking a running total. They're all very similar algorithms at the end. But remember how I was saying your linear search is your first like real general purpose algorithm? Yeah, it's going to pop up everywhere now. Turns out, going over a collection of things, a linear collection of things where there's a beginning, there's an end, and next has a natural, you have an idea of what next is because it's just natural. What comes after 0? 1. Why? Because it does. So going over this linear collection is a very natural thing. You're going to be doing a lot of that in programming. Let me zoom in. All right. Now, tuples, dictionaries, and sets. These three ideas, before I get into this, I want to be very clear. These three ideas are very important ideas. And we will be using dictionaries, tuples, and sets. We will. But in comparison to your general purpose list, you're going to be using these a fraction of the time compared to a list. I'm showing you what these are so you know they exist, so if and when the time comes that you want to use them or I ask you to use them, you know of them and you can do enough digging on your own to find how to use it the way you need to use it. But tuples, dictionaries, and sets. And probably the most important one of these would be dictionaries. Dictionaries are phenomenal. All right, a tuple. So, okay, a list is a linear data structure. Tuples are very similar to lists, but they're a lot more lightweight. They don't have a lot of methods or anything that goes along with them. With lists, we do. We have like all those methods attached to them, like append and whatnot. Tuples are just a way to group some information together, quick and easy, that's it. A list, you can do the same thing with a list, but a tuple is even more lightweight. I believe in assignment 1, it was tuples of latitude and longitudes, right? I think in assignment 3, I might have you working with tuples, I can't remember. But a tuple is just like a list in terms of how, you might create it. Instead of square brackets, we use parentheses. Right? So there's a tuple 10, 11. There, if I print it out, we see parenthesis 10, 11. We would see that. I'm going to go show you. A equals 10, 11. Print A. 10, 11. There. That's the tuple. And we can index the tuple. The tuple at index 0, well, that's 10. We can index it just like a list. And then your natural next question might be, well, is it mutable or immutable? So let's see. A at index 0 equals 77. Print A. Okay, it doesn't work. Tuples do not support item assignment. So this means tuples are immutable. Once they're created, you can't go into the tuple and change anything about it. just like a string. You can't go into that string and change anything about it. If we really want to change the values in there, well, we can't, but what we can do is make a new tuple, but just make sure to, when creating it, put the new value we want in there. And count and index. Those are the methods we get. There's not a lot there. We have A equals A dot. And look at all the methods we get for lists. There's a lot more. And they're mutable. So there is a difference. Tuples are more lightweight, and their general use are for quick and dirty ways just to group some information together, really handy, and then you can unpack it if and when you need it. That's the point of tuples. They're very, very, very lightweight lists that can't do nearly as much as a list. They're immutable, yeah. So here's the example from the Starbucks thing. Great. Any questions about tuples? A cool thing about tuples are Python will, by default, throw things into tuples if there's ever multiple values that are kind of like sitting in place of like a single value. What I mean is, if I were to say def some function, and the function just returns 4 and 5 because why not? This is a ridiculously simple and useless function. But see how here I'm saying return. Now, a function can only return one value. That's the rule. You are not allowed to have a function return more than one thing. You can't. That's against the rules. But what we can do is say this, return A and B, or 4 and 5. And you're going to say, well, that's two things. You just said you can't return more than one thing. No, what this is doing is returning one thing. Q equals ASD, print Q. It returns one tuple with two values in it. So Python automatically kind of threw something in a tuple there for you. It's kind of cool. And tuples, really one of their most common uses is, yeah, maybe you need your function to really return two things. So you just do it like this and it returns a tuple. Great. What's kind of cool too is in assignment, if I do this, it's smart enough to unpack the tuple positionally. So the first value gets stored in the variable Q and the second value gets stored in the variable P. Just neat little trivia. Not something you need to memorize or really be overly aware of. It'll pop up eventually, you'll get used to it. Neat. Any other questions or comments, thoughts of tuples? Yes?
Do tuples work in the same kind of way that a list would, like how it's being referred to?
Like an alias?
Yeah.
I gotcha. So well, here's where it would be kind of hard to check that. Because tuples are immutable. Meaning, you can't change them. So, let me show you what I mean. If I have a list, A equals A, B, C, B equals A at index 0 equals X, print B. And obviously B has been changed, except B wasn't changed. It's just the thing that B was referencing got changed. And this is the example of aliases and how it can seem weird, but it's just important to remember what is B actually holding. It's a reference. A and B are holding a reference, not the list. The reason this would be difficult to kind of test is the data is immutable. I'm not allowed to change it. So if I have A, B, C, by the sheer fact of it being immutable, I actually don't need to worry about like, oh, is it a reference or is it the value? Because by making it immutable, I can't change it anyway. So even if it was an alias, I can't accidentally mess up the data by having multiple references to it. So you might remember last week or maybe the week before when I was talking about mutability and immutability and how sometimes we actually like when things are immutable, when you can't change them. Well, it's to hedge against situations like this. When you have something immutable, you can't accidentally have two references and you mess up the data structure through some other alias. So interesting question that also highlights the value of making things immutable. Now, sometimes you really do want things that are mutable. Well, then you wouldn't use a tuple in this situation. Now, to answer your actual question, is it going to be an alias? Yeah, it would be an alias technically, but you wouldn't know. In fact, I'm not 100% sure it's an alias, but based on everything I know about Python, I can only reasonably assume it is. Someone could look that up. Someone do a quick Google search for that. Are tuples stored by reference in Python? And see what the answer is. If it's a reference, it'll be an alias. Okay, dictionaries. Here, you know what? I'll do that. How to store functions? No. All right, I didn't find a quick and easy answer here. I'm sure if I'd spent more than 30 seconds looking at it, I would have, but I can only assume it would be a reference just because of how the data is stored, right? It's like a collection of data, and I can't store all that in one variable. Yeah. Yes?
I looked up, are tuples stored by reference? Google says tuples store access to points to other objects or references.
Yeah, so it'd be a pointer or a reference. So the actual thing stored there is reference to the actual data we care about, like lists. Cool? Cool. Interesting question, though, because it gets a chance to highlight the value of immutable things. Okay, dictionaries. This is the important one. Of the three things we're talking about, now sets are kind of just basically dictionaries as well, but dictionaries are the super important one we're going to learn about. These are data structures that are insanely powerful. And I'll give you an example of why they're amazingly powerful after I explain them. So dictionaries are a little more sophisticated than a list. Now with a list, lists have an ordering to them. Index 0 followed by index 1 followed by index 2. There's an order to the elements in a list. And you index the list based on those values, those integer values. 0, 1, 2, 3, 4, right? That's how you index it. A dictionary actually allows you to store things in a collection, kind of like a list, kind of. But instead of indexing the things based on 0, 1, 2, 3, and so on, we index them based on whatever we want. For example, strings. So maybe I have a dictionary here to store grades of students. So I could have a list that is like, okay, 0, and let's say it's alphabetical, so I know 0 is someone who has the first name alphabetically in the list, followed by 1, 2, 3, and whatnot. But I could also store their grades in a dictionary where I index them based on their names. Or maybe something like their student number, whatever. Maybe student number is better because I know those will be unique. But I could do it based on names, which are strings, not integers. Which is neat, right? So to make the dictionary, I could start with an empty dictionary, and you see I use the curly braces, the squiggly brackets. And then to add something to the dictionary, I just go to like index it with the thing I want to add. So Billy doesn't currently exist. But I'm going to say, okay, my dictionary at index Billy is equal to 74. I'm going to copy this code so we can tinker around with it. So if I print out the whole dictionary, I see something like this. And you can actually create a dictionary that's not empty by doing similar syntax, but that's not important right now. So I added a few things here. If I didn't want some dictionary, if I only wanted one specific thing, I could say, okay, salad. And it would give me 88. So you see, I'm indexing this dictionary, not with an integer, but with the value of what we call these are keys. The key. I'm indexing it with the name Sally, which is the key for the dictionary. And that key has assigned to it the value 88. We call dictionaries key value pairs. Yes?
Can you use like a concept to set like a unique key that just keeps running as a new value is added to the dictionary?
Say the question again.
So as a new value is added to the dictionary, is it you can use a running total or concept to add a new key to every new reference in the dictionary?
I'm not sure I understand the question, but let me carry on and maybe I'll answer the question, then we can come back.
No problem.
So an important thing, and this may have been where you're getting to, a very important thing for the key is it has to be unique. You can't have two keys that are Sally. Once Sally exists as a key, that's it, you're stuck. Now, the values in the dictionary can be the same. There's no rule on that. We can set them all to 74. It's not going to matter. Like, that doesn't change anything. But the keys have to be unique. So perhaps using first names is a terrible idea because I'm willing to bet there are people in here that might have the same first name. So what would I do in that situation? Well, I'm in trouble. I would want to use something like your student number because that would be unique. Or your student login, like your code, because that should be unique. So this dictionary has 3 key value pairs in it. Billy, Sally, Jimmy, Bob, and they all have the same value, 74, because why not? But let's go back for fun. So to add them, it would be like I'm just doing an assignment on something that would already exist, kind of like in a list, right? There is no index Billy, but by just doing this assignment, Python goes, okay, well, they're adding the key Billy and associating it the value 74. Similarly with Sally and Jimmy Bob. And then to print it out, I can print out the whole thing, or I can index the individual key and get the specific value I care about. So that's really cool. Now, an interesting thing about dictionaries, although I think this is actually not true anymore in Python, but based on the abstract mathematical idea of a dictionary, certain programming languages call these things slightly different. Some call them maps. I can't remember what else other programming languages call them, but in Python we call them dictionaries. Unlike a list, which has like a nice ordering to it, there's the 0 index, 1 index, 2 index, and so on and so on and so on, however long our list is. Dictionaries don't actually have an order to them, which may be fine for your needs. But maybe if you really need something that has like an ordering to it, dictionaries isn't a good choice. So it kind of depends on your certain situation. So at this stage, the huge value here is suddenly I don't have to index my list with integers anymore. I can index something called a dictionary and have whatever I want to index the values I care about with whatever the key is. It's just the key has to be unique. But then again, same with list indices, right? List indices are also unique. You can't have 2 things that index 1, right? So, now did you have a question? I thought I saw.
No, I was thinking, is there any way to get a function instead of a dictionary
Store a function inside as the key or the value?
as the value?
Yes, you can.
But then, if he needs to have the variables, do you use the parentheses and you just put the value that needs to put?
Okay, you're asking a very interesting question that has a very nuanced answer that's not, I'm going to show you, but everybody, if you're thinking, oh man, I need to remember this, no, this is just like a cool thing you can do in Python. If you like it, great. If you want to never see it again in your life, you don't have to. So here's my dictionary. Let's go write a function called def sum a, b, return a plus b. Oh my goodness, what's going on here? Right, so here's my function, and then I can go back to some that the function equals sum. Great, so now it's in there. If I print sum dictionary, if I print it, we will see Billy, Sally, Jimmy, Bob, and the function, which is function, some function at OX7FE99E136200, which makes perfect sense. But we don't need to get into that right now. So if I were to index at the function, I would get just that function. But if I wanted to call the function, I would then add like the parentheses here and be like 2 and 4, and then I should get back 6. So I indexed the dictionary, which is the function, and then I immediately gave it the parameters, or the arguments 2 and 4, and it did 2 plus 4 because that's what some function does. Does that answer your question?
Yes.
Yeah? Now, for everyone else who's left going, what? Ignore everything I just did. If you found that interesting, cool. If not, you can ignore it. It doesn't matter. It's just a cool little thing you can do in Python. On that note, you can actually, I don't know if I showed you this earlier, you can assign A equals some, you can assign a function to a variable, and then just call like A of 5 and 6, nope, print A of 5 and 6, we see 11, because A is now kind of like an alias for the function, some function, which is weird, but you can totally do it. Other programming languages do not let you do this because this is kind of weird, but anyways, it's a neat little thing you could do. All right. So yeah, at this point, the value here seems as if it's, well, okay, instead of indexing based on integers, I can index based on whatever the hell I want. There are asterisks. The thing that you want to use as your index has to be what we call hashable, which is something we'll learn about way later. It doesn't matter, probably not even in this course. But dictionaries are great. Now, I'm trying to think of how to, do I have a good example in here? Why are they great? Okay, great, here we go. Okay, let's say, for example, I have this. I'm not using a dictionary here. I'm using a list of lists. I could have used a list of tuples, I suppose, here as well. But I've got a list of lists. What I want is I want to store grades for students in my class in a list, but each element in the list is going to be a pair of information. It's going to be the student name and then their grade, right? So my grades is the list, and the thing at index 0 would be Billy, 74, and then the list Sally, 88, Jimmy Bob, 99, right? And if I reprinted, I would see something like this. So this is a list of lists. The outside list has length 3, and each of the inside lists have length 2. Obviously, this is a very small course if I only have 3 students, but pretend there's 3 million students in there. I don't care. If I asked, I have a student named, and pretend there are a bajillion students in there, and I have a question. Okay, what is Steven's grade? How would I find it? What would I have to do? Well, to me, the simplest solution is, well, let's just do a linear search. Start at the beginning of the list at index 0. And then you take the list at index 0 and say, okay, tell me the thing at index 0 of that list, which is the name of the individual student, the corresponding student. Be like, okay, is this Stephen? If it is, great, I found it, I can return the internal list at index 1 to get the grade. If it's not, keep going. If I'm doing this linear search, okay, before I continue, does that make sense? This is a list of lists. It could have been a list of tuples, whatever, but it's a list of lists. The only catch here is I had to index the inside list to get the name to check for the comparison, right? There are 3 billion students in my class. How many things do I have to look at in order to guarantee, and assume the list is not sorted in any way. They're not alphabetical, they're just all over the place. How many things do I need to look at if this is a list of 2 billion, 3 billion, a list of size n? How many things would I have to look at in order to guarantee that I found them or conclude that they're not in there? All of them, all n. And if I double the size of n, I double the amount of work I have to do. Here with the dictionary, however, I could just go, my grade Sally, my grade's Stephen, and just get it. I don't need to do a linear search anymore. No need for that. You might be wondering to yourself, well, hold on. I know that, I could just call the function sum on my list. It'll give me the answer. But I know that really, if I open up the hood, I know that under the hood, it's doing that. It has to go through each element, right? So it's still doing that linear search. It just kind of hid it from you behind a function call, right? With absolute value or min or max. And that's probably what's happening here, right, with the dictionary. So with the dictionary, sure, you indexed it with the name, but behind the scenes, if I open up the hood, am I going to see doing a linear search for Sally to begin with? And the answer is no. It doesn't. Because of how they're built. And for better or worse, we're not going to get into how you build these structures in a computer. They're amazingly brilliant. You don't need to do a linear search. Meaning, if I had a class of size 3 billion, the amount of work it would take me is not 3 billion units of work to look at each individual thing. The amount of work I would have to do is just one thing, look up the dictionary. Is it there or not? If I double it to 6 billion, it's still only one thing of work I have to do. If I quadruple it, it's still only one thing of work. If I make n the biggest number possible, it's still only one unit of work, in theory. So suddenly, if you have an algorithm, let's say there's 2 students in here and you're working on assignment 7, which doesn't exist, and someone comes up with a solution where they're doing a linear search on lists of lists, and someone else uses a solution that uses a dictionary, the person using the dictionary has a far better solution. Both will be correct. If I do a linear search on a list of lists, it will give me the answer if it's there. If I do a lookup on the dictionary, it'll give me the answer if it's there. Both will give you the right answer. But one is a linear time algorithm. The amount of work you have to do grows linearly as the input size grows, which is just a fancy way of saying if I double the size of the input, I'm doubling the amount of work roughly. Because computer scientists are truly easy to get more precise than roughly. The constant time algorithm is no matter how big the input is, it's going to take the same amount of work. I don't care. So one of those 2 algorithms is going to be way faster than the other. If you have a choice to do a linear time algorithm or a constant time algorithm for the same problem, you would be the biggest fool on the planet to do a linear time one. That is, of course, if you're aware of the constant time one. Sometimes these constant time algorithms are not obvious. They kind of require kind of a clever implementation that you may not be familiar with. But when given the choice, you take the one with the better runtime, the constant time runtime. Did you have a question? Yes?
When you say work, you mean work done by the computer?
Yes.
Oh.
Because you figure that loop, right? For a linear search, that loop is going to run. How many times is that loop going to run? Once for each element in that list, right? With a lookup like this, there is no, here I need to call a linear search function, and I know in that function it's going to have a loop. Here, there is no loop. That loop, there's no loop that's going to run, ever. It's just going to be some code that runs, it just checks if it's there or not.
Isn't that a loop though? A code that runs and checks?
Nope. See, that's the catch, is you're thinking like, oh, well, I know, but under the hood, it's doing a linear search. It's not. Even though a lot of things so far, Python hides some things, and we can kind of assume, like, sure, if I use the max function, it tells me the biggest element in this list. You know that under the hood, there's an algorithm doing a linear search for the max. Here, you might be assuming, well, under the hood, it's doing a linear search. Under the hood, it's not. Under the hood, it's actually a brilliant implementation of an idea that makes this so fast. And I'll give you a very, 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 very high-level description of how dictionaries work. If I have a list of size 10, I just have a list of size 10. I have 10 things. I know how much room it's going to take up, whatever. But here's the idea with a dictionary, especially now space is cheap. All your computers have bajillion gigs of RAM and whatnot these days, so space is cheap. So here's what I'm going to do. I'm going to section off this giant chunk of RAM. Okay, this gigantic chunk of RAM over here. And I'm just going to kind of think of it as like a giant table. And each of these is a memory address. Whatever, it's a giant chunk of RAM. And we'll go like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on and so on and so on. Pretend this goes on forever. If this was a list, and I had 10 things in there, I would just store it like, whatever, right? But that's not what this is. This isn't a list. It's a dictionary. And a dictionary makes use of something called hashing. It makes use of a hash function. And a hash function, well, in computer science, we like to talk about a perfect hash function, which doesn't exist. But it's this idealized function. Some function that'll take some argument, some value, some parameter, whatever, and what it's going to do is it'll take that value and do some operation on it to have it come out to a number between 0 and, I don't know, let's say this is 100. It's not. But a number between 0 and 100. Okay? So if I say f of Sally, maybe this function gives me back the value 17. So it would go, okay, so 5, 10, 15, 16, 17. Sally's grade was 88, right? So I put the 88 in there. And it's great, because now I go, okay, if I want to use, what was the first name? Bob? Whatever. If I throw in Bob, if I put in Bob here, maybe this function gives me the number 82. I don't know, I pulled these out of nowhere, right? 82 for Bob, and let's say, I don't know, 82 is down here, and Bob had 74, I think it was. Right, so there we go. Now, that's my dictionary. I have 2 values in there. I know it's a ridiculously small dictionary, but I've got 2 values in there. Now, if I want to know, okay, let's find out Sally's thing. It's just a lookup. What's Sally's thing? I throw Sally through this function, which is just some basic number crunching. It's constant time. It gives me 17. I go down to 17, check is there a value there? Yeah, okay, it's 88. If there's no value there, well, I go, oh, well, I don't have a value for Sally. No need to search anymore because I have this special function that just tells me where to go in this giant lookup table. Pretty cool, I think. So there is no linear search anymore. There are 1,000,000,001 asterisks to this. This was a high-level description. Because you have something called collisions. There's no such thing as a perfect hash function, and maybe I come with the name Jimmy Bob, and it just so happens to give me the number 17. And then I'm like, uh-oh. 17's already used by Sally. What do I do? Get a better hash function? Come up with an interesting solution? There's a lot of issues there. But otherwise, it's just a lookup table. The downside is it uses a lot of space. The upside is it's a constant time now. I don't need to spend any time doing a linear search. This is great. So dictionaries are phenomenal. And they tend to be the trick in coming up with a better solution to a lot of problems. You're going to be using dictionaries on assignment 4, I think, maybe. This is not something you're going to be expected to be an expert in by the end of the semester. It's just something that I would expect you're aware of, as they're really cool. The big takeaway of this course, the more important data structure, most important data structure we're going to learn about in this class is lists. Lists, 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 lists. They're the big one. So did that get to your question? I think dictionaries are great, and you should too. Okay, so that's why they're great. So here was the example. Remember how some still required the computer to look at each value in the list, but the functionality was hidden from us? Yeah. Dictionaries are not simply hiding the linear search from us. They actually have some really cool functionality. We'll not go into more details, though, because it's outside the scope of this course. If you're wondering, well, what would the hash function be like? Well, I mean, you can make that up, right? Your hash function could be something like, we'll take each individual letter, right? And then maybe I map the letter S to which number of the alphabet that is. So A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S. That's 19. So I would take 19. I do A, which is a 1. I do L, which is whatever. And then I just add these up. And then there we go. There's my hash. Great. Now that's not going to be a good hash function because there's going to be a bunch of names that might add up to the same value. And you want your hash function to avoid collisions, but I really don't want to get into the weeds too much with these at this point. Any last questions though about dictionaries? Yes?
Wait, wouldn't using student IDs almost make a perfect hash function because they're all unique?
Well, you raise a very interesting question. So, what is, for example, don't tell me your student number, but how many digits is the student number?
8 or 9.
8 or 9? 9. 9.
9.
Okay. Meaning, I have, 1, 2, 3, 4, 5, 6, 7, 8, 9. I have a possibility of 100 million different student numbers, right? Now, all of those values aren't going to be used, but let's take a naive approach. So what I could do is just simply section off a chunk of RAM that's size 100 million, and then it's just a lookup table for each student. Great. The trouble with that is 100 million's a lot. So maybe what we could do, and I know that, does the university currently have 100 million students? No, we've got a hell of a lot less than that, right? Has the university over the course of its lifetime had 100 billion students in total? No, they haven't, right? So that would be a lot of wasted space. It would totally work, but it would result in a lot of wasted space. So maybe there's some math we could do to a student number to make it so the range of possible unique values is a lot smaller. And maybe we can find a really good hash function such that there won't be any collisions. But there's always those trade-offs. This is where we say there's no free lunch. Has anyone ever heard that phrase before? No free lunch? You win some, you lose some. There's pros and cons. So we can use more space and suddenly everything's constant time. But we use a lot of space. We could use less space, but it takes a little bit more processing power. There we go. It's kind of funny. And this is probably not really true at all, because if you think of the scale of large companies, but there was this idea when I was doing my undergrad of like, okay, we have this idea called time complexity and this idea called space complexity. Time complexity is like linear time algorithm. And space complexity is, well, how much space do you need for this algorithm to run relative to your input size n? And back when I was undergrad, no one really, they're like, space complexity, yeah, whatever, it's important, but no one cares. Everyone cares about time complexity. Which was never really true. People cared about space complexity. But in today's world, where you have like AWS storing insane amount of information, space complexity is definitely a really big important thing on the table that people like to talk about again. But these ideas are for next semester, next year. Very cool question though, nonetheless. An alternative could be, how many, okay, what is the structure of your student IDs?
The year that we...
So it's going to be like 22, and then like first, last name initials?
It was like 2022.
Oh, 2022.
I don't remember every just random 5 digits.
Oh, it's, okay, so how many,
5.
5. A, B, C, D, E. So, this part here is very regular. Every Every year is going to have its own thing. So I don't really need a lot there. But I have 26 possibilities here, 26 possibilities here, 26 here, 26 here, and 26 here. Isn't there like an XX in there or something too?
That's our email.
They're all numbers.
They're all numbers.
No. I mean, what is your, like, the pattern for your email?
Oh, it's X, the year you came.
X 2022 or just 22?
2022.
2022. That's
And
stupid.
3 random letters.
And then how many?
3.
3. A, B, C. So you figure this is always an X.
Yes.
This right here is very regular, right? Like, you could be like, oh, we need one for each year. No, we don't need records for St. FX students from the year 100, right? Like, we don't care about that. We know that this number here is not that important. So, how many unique sets of 3 letters are there? 26 to the 3 is the pattern you look for. Well, can someone type in 26 to the 3?
17,576.
So 17,000. Let's call it 18,000 because I'm lazy. 18,000. 18,000. Now, obviously, we need to account for the years. Fine. Just multiply that by how many years do we want to account for? 100 years? Fine. Okay, add 100 to this. That's 18 million. Well, suddenly that's a heck of a lot. 18 million? 180. No, that's 1.8 million. 1.8 million unique ones. And that's assuming we have 100 years. Maybe we really don't need to keep that much. I don't know. But 1 million is a hell of a lot less than 100 million, right? So suddenly with the different encoding, we can save a lot of space, which is kind of neat. Okay, sets. Sets are another linear collection, but they do not have an ordering, although they kind of do in Python, but they don't mathematically have an ordering. You just throw things into the set, and then you can check if the thing exists in the set or not. Great. And an interesting thing about sets are they only allow for unique pieces of information. If I add the name Bob to the set twice, Bob will only exist in the set once. It ignores duplicates. So a set is a great way to store information if you know you kind of care about uniqueness and whatnot. And another thing that comes with sets are, let's see if I have a good example here. Sets. Is I can do really good set operations on them. Who here, I don't even know, in algebra, discrete mathematics? Raise your hand if you've ever heard of sets in math before. Really? I feel like I learned that in like high school, but it's been a while, so I don't remember. Of course you have. When you did like in math and you're like for the range of all values, and that's a set, right? So you define the set of possible y values and x values for your function, right? That's a set, okay? And you can't have 2 values in your set that are duplicates. So there you go. What's cool about sets is we have these operations called set union, intersection, and difference. Set union is take everything from this set and everything from this set and put them together. If there's duplicates, whatever, you ignore the duplicates. If you have the set A, B, C and the set C, D, E, you union them, you get A, B, C, D, E. That double C doesn't matter. The set difference, or pardon me, the set intersection would be what exists in both sets. So if I had A, B, C, and C, D, E, the intersection would only be C, what exists in both sets. And then there's set difference, which is what exists in one set but not the other set. Order matters on that one. So this has some really good use cases. For example, I gave you a book that you could load into Python. It's just a giant text file of all the contents of Alice in Wonderland. And I ask you, how many unique words are there in this book? All right, just throw it in a set and get the size of the set. Because anything that's duplicated is ignored. So it'll tell me unique letters. Great. What if I gave you another book and asked, What words do they have in common? Well, you just load one into a set, one into another set, and do the intersection. Which ones they have in common? What exists in both sets? I wanted to know the number of unique words that exist between the two books. Okay, just do the union and get the length. I want to know what words are in one book but not the other. I could do the set difference. These are use cases. This is a very specific data structure that has very good use cases for what it's good at, but it's not great at what it's not good at. I'm going to re-hit sets tomorrow. Oh, I guess not tomorrow, Friday. Anyways, I'll see y'all.